So I'm Robbie, my colleague Colin Soames, who's involved in this work, and two other people, Yanis Katis, who's in the back, and a student, Pedro Her, who's not here at the moment. This is about diagnostics, and looking at identifying which antimicrobial to prescribe using a laser-based, low-cost, paper-based, 3D printed structure, which I'll show you. So, basic principles, the World Health Organization has defined diagnostics, so this nice acronym assured. Any diagnostics we use have to be ideally all these topical things here. Sensitive, specific, rapid, robust, equipment-free, deliverable to end users. A nice abbreviation there, assured. My addition to that is not quite so elegant as the word assured. It's MMEC, not quite so good as assured. Other things you might want to do: mass producible, certainly, mobile phone readable diagnostic, easy to use, certainly, cheap or ideally free, and home usable. So I'll show you some things we're using which can be used in the home as a diagnostic for detecting things. And this is the kind of the cartoon here. Ideally, such a scheme would involve some kind of diagnostic at home, maybe predominantly here, some tests you read, some coloured tests, and then a mobile phone can then read them. If they're simple tests like pregnancy tests, you want to know the answer straight away. If they're more complicated and have ethical overtones, then you want to be able to read them securely, but maybe you don't want to know them in your home. So your friendly doctor reads them, gives you a phone call from the hospital, and then the post person here can then come and give you another sample again, which you can use to test with a liquid, often urine, and maybe things like saliva, etc. So that's the kind of schematic of what we think of as a home-based test. An example which I know about, learned recently, pregnancy testing. So it's a lateral flow device, so urine goes here, and if it lights up 2 pink bars, I learn, then you're pregnant. If you only 1 bar, you're not pregnant. And this is 90% of the lateral test diagnostic market. Many people use these, very common, cost about £5. But this tests for only one thing: pregnancy. What it's designed for, are you pregnant or not? So, wouldn't it be nice, and we're trying to do this now, we could test for more than one thing. So, same kind of kit here, but we use a laser to write channels in this paper here. This is the paper in which urine will flow. But here you've got maybe a dozen, or maybe 10 or something, different flow channels. And by putting the right chemicals, biochemicals, antibodies, etc., capture antibodies on here, they can light up the different colours to tell you if you've got one of a range of diseases. Now, pregnancy is not a disease, okay, it's a condition, but you can have then more than one thing diagnosed at the same time. So multiple diseases, conditions, or biomarkers. The other thing you might want to do, however, is the following, is to be able to detect something but look at the quantification or the degree of severity. We can do that too. So the same test here, we put different levels of markers or antibodies, capture antibodies here, and you can see if it's light pink, you've got it to a low degree, and then the degree of pinkness, or whatever colour you like, can say low, medium, high. Go to hospital right now. You know, don't wait, as fast as you can. So you can detect one thing with different levels, or several things. Okay, so we're using lasers then to pattern paper. By paper I really mean membranes, like nitrocellulose, cellulose, a range of other things. A laser beam scans down here very quickly and polymerizes in the paper an impermeable wall. And that wall is then fixed and is firm, and liquids you put on here, drops of liquids here, will then flow down the channels, separate channels down here, and won't mix. So you could do, in this case, 6 tests in one, provided you've got the biochemistry on the far end to give the colour change. This is ink, by the way, it's not blood. It's just ink to show the things. But you put a blob of material here, and it flows down and doesn't mix. So our technique is very fast. You can write a metre per second of these things, and to write a device that I'll show you later takes about 1 second. So I said cheap, 1 second per device is pretty good. The laser powers you need are about the laser power and this laser pointer. You focus it down to a very small spot with a lens, and you can write there and polymerize a channel. And dimensions here are millimetres down to 100 microns like this. 100 microns is the diameter of a human hair. So you can write multi-channels inside a paper strip. You can write 100 different tests, if you will, in a 10mm strip. This shows, again, ink here has been flowed in here. This is a 1mm, 400 microns, 200 microns, 100 microns. It will flow down this channel inside the paper membrane. This is about 50 microns. It won't flow. So you can have lots of dense patterning if you wish. And that indicates, well, it would be cheap in the end. For the area of AMR, however, you don't really, well, you may want to have flow channels, you also may want to have wells. This shows just a crosshatch, a checkerboard of polymerized walls. If you've got different colour inks in these regions here, they don't mix. So if you could have the biochemistry inside this well area here, you would test for nine things. Or indeed, if you have a conventional kind of 8 by 12 kind of micro-titer plate array, you can test for 96 things at the same time. There's no limit. If you wish to have very small areas here, you can have hundreds or thousands of tests performed in parallel at the same time on a piece of paper, which you could then read with your mobile phone, your smartphone, and send the results in. You may want to know the results, you do want to know the results, but you may want to know it from medical backup. So, if you put liquids on these things here, they don't flow into the other regions. So this shows a kind of an analogy again of the micro-titer plate here, but different tests are going to be performed in those 15 or different areas. For the patient or the person at home, they would say, oh, test number A has gone blue, test number B has gone green, test number Z has gone red. So they would know the result, and they can then intuit it or send it in. So this kind of, if you like, may replace these kind of micro-titer plates here, which have a large volume, and the volume on our paper here is 1/100th of the volume inside these wells. Physically transporting this from A to B is quite hard. The patients will do this themselves and they can't really do it. This involves putting this in a cup of urine, which you can do, or other fluids, and so people can do that, whereas that is really an in-lab based kind of device. And you may have biochemicals inside already, preconditioned. So this really resides inside a lab, the other one resides inside a home. So looking at paper-based testing, we think this will allow early stage detection, because you can get this in the post sent to you. It'll free up clinician or GP time, because you do it at home, then you come back and you then engage your GP or clinician, leading to prevention, we hope, of AMR, via this. Our solution is the following. These are kind of conventional Petri dishes here, and there are schemes where you can dose this up with various levels of materials, let's say biochemicals, samples, and you can look for the growth of bacteria here inside your plate. It gets quite complicated, but you've really got to interpret this by experts. So with our approach, we write different patterns here inside the porous membrane, and then you can dose these up with samples. You dip into a common, say, sample like urine, and you can look for then colour changes. So if you will, it's analogues of these agar culture plates, but in bulk. So what we do, last slide, to show the detection of pathogens here, you take a piece of paper or other membrane, you pattern 9 or whatever number you want. Then you can do inoculating, incubating, and readout. And by the colour change here, you can detect either what you've grown, so you can see what has been allowed to grow, hence detecting what bacteria are present. Or, if you dose these up with antibiotics, 9 or 10 or 100, and you can see which have grown, you then know, this, I've worked at, I've got this particular infection or this particular bacteria, and it's resistant to this antibiotic. So you know in advance what it is, you can go back to your doctor or GP and say, I want to be helped with. And at home, of course, you might want to culture this, so you've got to go to IKEA, you've got to buy a lamp here, so this is or other shops are available. So you can then heat this gently at home for 10, 12 hours, and then you can culture it at home. Last slide, I said before, second last slide. You can also do it on other materials here, not just cellulose or glass fibre, etc. Other fabrics, pads, sponges, bandages, etc. And patterning here inside fabric for smart bandages that tell you you've got an infection by colour change, we think is a good deal. Smart plasters. So in summary, paper-based or porous media-based platforms for rapid diagnostics. And home testing is the market we're looking at. Cheap, of course, very fast manufacturing devices. We have a nice EPSRC grant here, which has just been able to fund this, and colleagues in the audience in medicine and other places are working with us. We think we need to demonstrate it works now in practice for AMR, so we need the help of medics, and you quantify sensitivity, but with a range of wells here, you've got 100 or 1,000, you can have various degrees of sensitivity in the X and Y directions. So we need to validate the concept for future AMR work. That's it.